Hello and welcome everybody. Today in geometry we will be discussing perpendicular lines in a plane. So this one is going to be a little hefty, so grab a seat, grab a drink, and grab some food if you need to. So here we go. So as I said, we are going to be focusing on perpendiculars in a plane. To be a little bit more specific, lines that are perpendicular to each other through an internal point and also an external point. We'll be looking at more specifically the perpendicular bisector and also something called the perpendicular bisector theorem and its converse. So let's go ahead and get started. The first thing that we're going to look at is this one called Theorem 6-1. And since it doesn't really have a name to it, then you can kind of suspect that you're probably going to see this maybe 3 or 4 times a little bit later on, because this is going to be a proof that we're going to be used to prove something that is going to be more important. So here's what it says. This theorem says that if you have a given plane right here through a given point of a given line, there exists one and only one line that is going to be perpendicular to the given line. So in terms of what that is saying, because it sounds like very cryptic, what it means is you're going to have a line L right here, as you can see on the right hand side. So here's that line L, and on that line L we're going to go ahead and have a point which we'll go ahead and call P. This theorem basically states that there is going to be only one and only one line, we'll go ahead and call M, that is going to be perpendicular to L at that point P then. Now, because of this right here, where it's this one and only one, then that means that we have to prove existence and uniqueness, as we mentioned a while back. So then that means that there are basically 2 tiers or 2 layers to this proof. So first, what I did was I kind of wrote it as a restate underneath. If you want to take a look at it, that's totally fine. Let me just kind of reiterate so that it's a little bit more, so then we can write a proof according to it. So let line L be in the plane with point P on the line, just as we said. Then there exists one and only one line M, such that M is perpendicular to L, and the intersection of M and L is supposed to be equal to P. All right, so here's the proof for it. Instead of going through the whole statement and reasoning, let me go ahead and kind of reiterate on the side as to what's going to happen then. So first, what we're going to do is we're going to go ahead and draw that line L right here, as we said, and then we're going to go ahead and draw a line, we're going to go ahead and introduce point P that is over here. So next, what we're going to do is we're going to go ahead and introduce a point that is up here. We're going to go ahead and call X. That is basically the first part of it. So we're just going to go ahead and introduce that point X. And so let's see. In addition to that, we are going to introduce another point that is going to be, oh, actually, wait, I'm sorry, I kind of messed that up, so I apologize for that. Let me go ahead and introduce a point X that's going to be on line L. That is my fault right there. And the point that is on the upper part, or the upper half of it, we're going to go ahead and call that point Y right there, okay? So all I'm doing is I'm just introducing points. And the reason why I'm doing that is, if you notice, with 3 points, we can form an angle. So here, that is what that angle is going to look like. And in terms of where that is located, if you remember something called the angle construction postulate, there should be only one angle such that that numerical value is equal to 90 degrees. Okay, so then that means that by introducing point X and then introducing point Y, there should be a Y somewhere out there that the angle is going to be 90 degrees. And right there, I have basically shown that there exists the perpendicular then, because of that angle construction postulate. So because this is 90 degrees, then therefore it's a right angle. And as a result, if it's a right angle, then therefore it is perpendicular. Okay, so that's the existence part. Now, for the uniqueness part, is basically kind of the same thing. So what you're going to do is suppose that there are going to be 2 lines that are going to be perpendicular to line L. We're going to go ahead and call it M1 and M2. So meaning in the uniqueness part, we're going to have something that looks like the following. You still have that point P that's over here. But this time around, I'm saying that there is going to be one line that is perpendicular to P over here. And then you have another line that is going to be perpendicular to P that's over here. we still are going to preserve that point x test on the side. And let's go ahead and call this over here m1, and then let's go ahead and call this over here m2. Now, needless to say, that looks really ridiculous because you should be able to recognize that those two lines are going to be the same thing. Well, just to make sure that we are going to get the same thing, let's put it this way. Again, under the angle construction postulate, then that means that we can say the following. Since this is supposed to be a right angle, then that means that there is a 90 degrees. Since this is also going to be a 90-degree angle, since this is also equal to a right angle, then it's also equal to 90 degrees. Then according to the angle construction postulate, there exists exactly one line or one ray that contains them. So therefore, these two lines must be one and the same because there's no way for there to be two lines for that to happen. Remember, for every angle, you can only assign one exact unique ray, and that's what's happening here. So that's going to be my proof then, okay? So if you want to take a look at the statement and reason form, you can go ahead and do so, but I think it's probably a little bit easier if I just drew it out as an illustration. All right, so now we're going to go ahead and move on to the next part, which is something that is going to be pretty important and we're going to be using quite often. So this right here is going to be, first of all, the perpendicular bisector. What is it and how do we actually use it then? Okay, so first off, definition, what is a perpendicular bisector? Let line L be the perpendicular, that's what PB stands for, not peanut butter, of a segment AB. And if the following is true, then that means it's a perpendicular bisector. L, that line, is going to be perpendicular to AB, the segment. And in addition to that, L, the intersection with AB, is going to be the point M, where M is going to be the midpoint of AB then. So you can see then, underneath over here, I have drawn a picture. Actually, you know what? I'll draw it over here on the side. So let's say that we have point A and point B, as we said, right? The line L, which is going to act as the perpendicular bisector, according to what it said, is that, first of all, it's going to intersect AB at some point M. And that point M is supposed to be the midpoint. So that means that these two right here are congruent. And in addition to that, it is perpendicular to the line that's right there. Now, something that's really interesting that you might know is that, or we might discover, is that if I take any point on this perpendicular bisector, it definitely looks like it's going to be equidistant to the endpoints over here. And in fact, that is what is known as the perpendicular bisector theorem. And that's what we're going to look at right now. So here it is. This time around, we say that let L be the perpendicular bisector of AB on plane E, just as we said. Then the perpendicular bisector theorem says that for any point that you pick on this line L, the perpendicular bisector, it is equidistant to the endpoint PA and PB. So if I were to draw that out right here, hopefully you can then kind of see as to how the proof is actually going to work out. So all the markings are there for L to be perpendicular bisecting. I want to know if PA is actually equal to PB. So that's where I'm going to put the question marks. Well, judging by what we have, it looks like we have two congruent triangles because of SAS. And so then that means that triangle PMA should then be congruent to triangle PMB by SAS and by corresponding parts. Then yeah, definitely these two are going to be congruent to each other. Okay. All right, good. So that right there, that is going to be proved by SAS. So that's the easy one. Now, here in the perpendicular bisector theorem, we are also going to include its converse. So here the converse is saying that, hey, if I have a point P, that is going to be, oops, I accidentally erase it. Hopefully I didn't erase it. Well, let's see how it goes. If I have a point P such that PA is equal to PB, then P is going to be on the perpendicular bisector. So what that means this time around is that, let me go ahead and change the picture a little bit. Here, I am going to go ahead and erase this marking right here, and erase this marking right here, and this marking, and so forth, okay? This time around, what's going to happen is, I just know that PA and PB are supposed to be congruent to each other. So then that means that we have these two are going to be congruent to each other, and everything else stays the same. I want to know, is this guy going to be the perpendicular bisector? So that is to say, my question mark over here is we actually don't know if this is going to be a right angle. So that's where I'm going to go ahead and put the question mark and put the question mark. So that is going to be our setup for the converse. Well, looking at the picture once again, I think we've got enough practice from chapter 5 to see that these two triangles are also congruent to each other by SSS this time. And if that's the case, then that means that this angle should be congruent to this angle. And if those two angles are congruent to each other and they form a linear pair, which they do, then that means that by theorem 4, then that means that they should be forming a right angle. Then that means that both of them are going to be a right angle then. Or actually, I think it was like theorem 4 too. Sorry about that. I got it mixed up. And hence, that means that, yes, it is going to be perpendicular. So this one right here, the converse, we can definitely prove by SSS. Okay? Now, if you want to write out the proof for it, that's totally fine. But I figured that, you know, by saying it out loud like this, that might be able to help you understand a little bit faster. And you can always just go back to recording to just to if you can always go back to the recording if you don't understand a certain part. All right. So next, now we're going to look at this corollary right here, which is going to be kind of like a small little theorem that we're going to be using to prove something that's a little bit more important. Okay, so hence, that's why it's called a corollary. So here's what the corollary says. Let segment AB and line L be on the plane E. If C and D are points that are going to be on line L, such that CA is equal to CB and DA is equal to DB, then line L is the perpendicular bisector of AB. So without looking at the picture on the right, let's just go ahead and kind of start from the very beginning as to what I'm talking about. Let's say that we have a point A and point B, as we said. Okay. Next, what's going to happen is we're going to go ahead and have a point. We're going to have a line L somewhere. Okay, so we're going to have somewhere. We're going to go ahead and call that line L. And on that line, there are going to be 2 points. We're going to call C and D. Now, L is not necessarily located over there. It could be somewhere else. But what we do know is that the point C to A and the point C to B are equal distance. So then that means I got to take this guy right here and I got to position it somewhere such that it's true. So maybe somewhere around here then. Okay. So I'm going to put it over there because we know for a given that this right here should be congruent to this right here. And similarly, this right here should then be congruent to this right here. Maybe I could draw D somewhere else so then that way it's a little bit longer. And in fact, you know what? I think I'm actually going to do that just to make it so that it's a little bit easier to see or easier to swallow. So let me go ahead and put D maybe like a little bit further down. Give me 1 second. My iPad is kind of slowing down and dying because, you know, of old age. But anyhow, D's down here. Okay, so you can see that another given is that these two guys are going to be congruent to these two guys. So the conclusion, according to this corollary, is that L has to be the perpendicular bisector of AB. So then that means that if I draw AB right here, right, I basically need to show that this is going to be congruent to this, and this right here is going to be congruent to this. Okay. All right. So let's go ahead and take a quick proof on the right hand side. So then that way you can kind of see how it works. Let me go ahead. Wow. Sorry about that. Let me go ahead and erase all of this over here because I think it might be actually better if I just kind of started from scratch. Okay. So here's what I will do. Okay, and again, we're not going to go ahead and write it in statement and reason because just to kind of like, so you can actually visualize all of this without having to like, you know, grind it all out. So let's get that line L over there, okay? And some point on there is going to be C. Now remember, B is going to be some point that's out there. So let's go ahead and put B somewhere over here. And there's going to be a certain length, which is going to be that first mark that you see. Here's what I'm going to do. You notice that L is basically kind of like a divider for our plane, which is going to be this board that I'm working on. What I'm going to go ahead and say is, let's go ahead and create A. Okay, let's go ahead and find A over here, such that, yes, these two are going to be congruent to each other, as it says in the given. But also, I'm going to go ahead and put A so that it's located at a place where these two angles are going to be congruent to each other. Because technically A, I can go ahead and put it like right here if I wanted to, or right here if I wanted to, or right here if I wanted to, so long as all the lengths are the same. But I want it to be in a certain specific place. So then that way I can kind of set up what I need to do next. Okay, so first I'm going to go ahead and put that in there. Okay, and let me see if I can erase that a little bit better. So once again, we have point C over here. And we're going to go ahead and introduce the point A so that it is going to be such that this angle right here is going to be congruent to this angle right here. Now, once that is done, what I'm going to do is I'm going to go ahead and introduce AB, and you'll notice that there's going to be a point of intersection between the two lines over here. So we'll go ahead and call it M if you want to, okay? Let's see. Looking at those two triangles, I do believe that they are congruent to each other by SAS because the middle segment is shared because of the reflexive property. So by SAS, these two triangles are congruent, and hey, just like before, then definitely I know then that means that this angle right here would then be congruent to this angle right here. And because they form a linear pair, once again, then that means that we have some right angles right there. Very similar to the proof that we just did, right? And moreover, then this guy right here is going to be congruent to this guy right here because of CP/CDC. So there it is. Now we prove that that line that contains C is going to give me the line that contains C is going to be the perpendicular bisector. Now, we need to actually do that same thing with that point D that is somewhere down here. But I'm thinking, you can kind of see what's going to happen. My proof for this is probably going to be exactly the same thing. We're going to go ahead and choose D somewhere over here, and then we're going to go ahead and create BD. And then we're going to go ahead and create a point A over here on the left-hand side such that these two are going to be congruent once again. And then by SAS, once again, we can have the exact same setup. So therefore, the bottom triangle will also be congruent to each other by SAS. And then therefore, you can see the perpendicular bisector part. Okay? All right, so that's going to be our corollary, which we're definitely going to be using very, very soon. All right, now let's go ahead and scroll up to the last part of it, and this is going to be near the end, and this is probably the big part that is that we're all been waiting for. And by the way, if you're wondering how come I am kind of like scrolling up instead of normally scrolling down, it's because when I first started writing this, I accidentally started on page 20, as you can see, kind of like on the bottom. So, well, my little mistake, if anything. Okay. All right, so here it is, the last part. Theorem 6-3. Okay. Through an external point this time, we're looking for the perpendicular. So this time around, here's what it says in this theorem. Through an external point of any given line, there exists one and only one line perpendicular to the line containing the point. Very similar to that of Theorem 6-1. But the difference between 6-1 and 6-3 is that the point is not going to be on the line. So you can see it, that's right here on the right-hand side. So here in the picture, let me just kind of like, erase this. Oh, I can't erase it. But you'll notice that there you have, once again, line L. This time, point P is not going to be on line L, but it's going to be somewhere external out there. And this theorem says that now there's only going to be one line that is going to be perpendicular to L containing P. So then that means that there is going to be that setup then. Okay. Well, just like in Theorem 6-1, because of this right here, one and only one right here, then that means we have an existence and uniqueness proof then, okay? So let's go ahead and see if we can prove this. And yeah, let's go ahead and go at it then. So here, once again, I'm going to go ahead and write it as a restate. So for the sake of coming up with a proof, the restate is going to be given line L and point P on the plane such that P is not going to be on L. There exists one and only one line M, that M is going to be perpendicular to L, and also P is going to be inside that line line M. All right, so here it is, the existence proof. I think you can have an idea as to what's going to happen here. We're going to go ahead and try to create some angles so then we can see how this actually works out. So here we go. Let's go ahead and do something here. First off, what I'm going to do is I'm going to introduce a point that is going to be on line L. Not necessarily right below it, but just some point. Let me go ahead and call this point Q over here. Okay, so that's going to be my point Q. And as you can see, we can go ahead and form a segment from here to here then. In addition to that, let me go ahead and pick another point over here. We're just going to go ahead and call R. Doesn't matter where is it. Okay, but you'll notice what I'm doing right now is, once again, I'm going to form 3 points. So then that way I can create an angle right here. Now, with that angle, think of what we did for the last proof. I created another ray down here, right? And we can always do that, such that this ray is going to be making an angle that is going to be congruent to the one that I just formed. Okay, so I'm going to create another ray that's going to be down here that is going to be congruent to the angle that I just formed. In addition to that, I am also going to go all the way out to a point on the ray. We're going to go ahead and call point, I don't know, let's go ahead and call it T, okay? Such that these two line segments are going to be congruent to each other, okay? So I'm going to do quite a bit over here. First of all, I created this angle, right? And then afterward, I am going to create kind of like a reflection underneath of it. So we're going to first create an angle that is going to be the same as this angle up here, okay? And I'm going to go out in that ray by a certain distance. We're going to go ahead and call T to some point T, such that QT is going to be congruent to QP. Well, once again, just like before, I can now go ahead and form this line right here. And if you look at our picture, then we definitely have two triangles. Let me go ahead and call this point U if it helps out here, okay? Looking at the two triangles, they are going to be congruent to each other by SAS because they share QU by reflexive property. So by SAS, these two triangles are congruent, and therefore, then that means that this angle PUQ is going to be congruent to this angle TUQ. And hey, looking at what we have, TUP, they're all straight collinear. Then that means that those two angles are once again linear pairs, making these two angles congruent to each other. So therefore, we're going to have that right angle. Who knew that this thing would come up so often from back in chapter 4? But hey, there you go. We're all set. Okay. Remember in Theorem 6.1 right here, right? Through an internal point, right? A point that is on line L, there exists a line that is going to be perpendicular to it that's going up. And that's exactly what's happening over here. So right there, I have showed the existence part. Now I want to show the uniqueness part, meaning that there's only going to be one line that is going to be perpendicular to L going through P. So now let's go ahead and draw that down here. So in my picture for the uniqueness part, we're going to go ahead and do it by indirect proof, just basically kind of like what we've been doing so far, anytime we want to show uniqueness. So what's going to happen is I'm going to go ahead and assume that there are two lines that are perpendicular to L that goes through P then. And you can probably guess it's going to look really funny, okay? So here, let's go ahead and say we have one line right here that is perpendicular to L. And that is going to, let's say, intersect at some point. We'll go ahead and call M1. Now, I'm going to go ahead and do the same thing over here. We are going to find another point, okay? That is going to be the intersection of the perpendicular and line L going through P. And then that means that this is going to be a right angle as well. Well, needless to say, how silly that looks. Definitely, that is not something that is going to be possible because, again, if you remember what we said earlier, right? According to Theorem 6.1, the one that we proved earlier, for any point that is on the line L, that's internal on line L, there exists exactly one line that's perpendicular, right? So here is going to be one line that's perpendicular. Let's go ahead and call it L1. Let's say that over here, we're going to go ahead and call that L2. Well, both L1 and L2 are going to contain point P according to the given, and right there, that in itself is a contradiction. So then that means that L1 has to be equal to L2 because of Theorem 6.1. I think we can actually pull something that might be useful in the future out of this. Here is the last part, the corollary 6.41. No triangle is going to be able to have two right angles inside, right here, just as shown in the picture.